Hi everyone. In this video, let's introduce the atom and then talk about electricity. Okay, atoms are the tiniest particles that make up the world around us. So all matter is made up of atoms. And if you could inspect an atom, you would see that the atoms are made up of three smaller pieces called protons, neutrons, and electrons. Okay, and these fundamental particles that make up the atom, we need to know a little bit about them, and it'll become more important when we get to the chemistry section later in the course. Okay, protons. Two ideas that you need to know about protons is that they have some electricity associated with them, a positive charge, and they are found in the middle or the center of the atom. And there's a term for the center of the atom. It's called the nucleus. Also found in the center of the atom are neutrons. And these neutrons, they don't have any charge. They're zero charge or neutral charge or just no charge. And it turns out they weigh about as much as a proton. So they have about the same mass. The third particle is the electron. And electrons, well, it sounds like electricity, so we need electrons to talk about electricity. Electrons have electricity associated with them. They have a negative charge, and the electrons are actually found flying about the nucleus. And in terms of mass, they are really tiny. It takes about 2,000 electrons to weigh as much as a single proton. So the electrons are really, really tiny in terms of mass. And there's a couple pictures, kind of get the idea of what an atom might look like. If you could see one, in the middle, you got, well, the middle is called the nucleus. In the middle, you have all these little tiny protons. They have plus charges. And there's other things that are just adding weight, just dead weight, because there's no charge associated with the neutron. And then flying around are the electrons. Sometimes we think about them going in little orbits. That's, it's useful to think about that. We'll talk about that in chemistry. But let's kind of dispel that idea. If you think about electrons going in a flat circle, that would make for a flat atom. Atoms are not flat. They are three-dimensional. You can kind of think of them as little balls. And so maybe this idea, kind of spinning in and out of the plane of the paper, just occupying all the space around in a big volume, a big sphere. We also need to know something about these electrical charges. Electrons and protons have opposite charges, and opposite charges attract. And then like charges repel. So the little electrons flying around the atom, they don't like to come together. They repel each other and fly apart. Oh, and then how come the protons are all tucked away tightly together? Well, there's another force in there that's holding them together. And when we talk about nuclear power, we'll talk about harnessing the energy of that attractive force in the nucleus. It's a really strong force that's holding these all these protons together, despite the fact that they have the same type of charge and they want to repel each other. Okay, in a previous chapter we talked about the conservation of energy, and we said energy is neither created nor destroyed. The same can be said for charge. Charge is neither created nor destroyed. Okay, one more idea here. To get an idea how big an atom might be relative to the protons, neutrons, and electrons, this is a good picture. This guy's holding a tiny little ball bearing in his hand. And it turns out that if you could shrink yourself down to the size of an atom and actually put your fingers around the nucleus, then look around and see where those electrons are flying around. They would be flying around in the volume the size of the stadium. So even though the electrons are attracted to the protons, and they keep trying to strike the protons in the nucleus, that's a really tiny target. So the electrons are free to roam all over the stadium, close to the nucleus, farther out, all the way out to the nosebleed seats up there. They're all over the place. And an atom essentially is empty space. It's just room for the electrons to fly around in. And they keep coming back towards the nucleus as they're attracted to them, but they keep missing. It's a small target, and they fly away and get pulled back by the attractive forces. And then the electrons are just in constant motion. Let's now talk about electricity. Electricity. is the flow of electrons. And when we think about electrons flowing, perhaps in an electrical wire, there's three ways you can talk about how these electrons are moving. You can talk about, just the sheer volume of all these electrons flowing, and that's called current. And the unit for measuring current is called amperes, abbreviated with an A. We can also talk about how hard these electrons are being pushed along. The electric potential is called voltage, and we measure that in volts, abbreviated with a V. And then as these electrons travel through a wire or through other things, we'll talk about some other things electricity could flow through, that material the electron trying to flow through, they resist the flow of electrons. And that resistance is measured in ohms. And it's got the Greek letter omega to symbolize ohms. And those are the three key properties when we talk about electricity. Your book kind of compares electricity and wires to that of water flowing through pipes. And I think that's a good analogy. So if you think about electrical current, that's analogous to how fast is water flowing through the pipe. If you want to talk about voltage in an electrical system, that's sort of like the water pressure. So how hard is the water being squeezed through this pipe? Is it a low pressure or a high pressure? That's analogous to low voltage, high voltage. And then resistance in an electrical system, that's sort of like the diameter of the pipe. If the pipe was really big, then the water could flow out more easily. There wouldn't be much resistance. But as you narrow down the pipe, make it more narrow, there'd be a lot more resistance. It'd be more difficult to get the current to flow, get the water to flow through. And then finally we have Ohm's law, which relates all three properties together. And one way you can write Ohm's law is in terms of current. How much electricity is flowing through a wire? Well, that's proportional to how hard it's being pushed through the wire. It's proportional to the voltage. So higher voltage means more current. But resistance is opposing the current. So the more resistance you have, the less current you have. And then in math, what we do is we divide by the resistance. So you can measure the current if you know the voltage and the resistance. And of course, you can do some algebra. So as long as you know any two of these values, you can calculate the third one. Okay, let's talk about electrical currents. There's two ways you can get electricity to flow through a wire. If you use a battery, the electrons come out. Right? Atoms are formed of electrons. Electrons are on the outside. They can move from one atom to another within the copper wire or whatever material the wire is made out of. And electrons just flow in a continuous stream through that wire to make its way back to the battery, to the positive end, right? So the electrons, if I abbreviate it as E minus for electron, that's negative, they're attracted to the positive charge, so they're drawn in this way. And at the bottom of the battery, that's the negative side. The electrons are repelled and pushed out of the battery. And electricity, the electrons just flow in a single direction all the way around. And as electrons enter the light bulb here, they go into a wire that offers a lot more resistance. And the electrons then are trying to push through this wire. Maybe it's made of tungsten instead of copper. And the electrons bump in that material. They slow down and they start heating up. They're trying to push their way through the tungsten. They heat up the tungsten until it's white hot and it starts to glow and gives off light. And also gives off heat too. There's another way that electricity could run through a wire, and that's where it runs back and forth. So that's what these little double arrows are representing. That in one moment in time, the electrical current is moving, let's say, to the right, and then in the next instant, it moves back to the left, and it just cycles back and forth. Left, right, left, right, left, right. And the electrons just kind of bounce back and forth, up, down here. And why is that? Well, a battery is used to kind of generate the electrons and make them flow. And that's a direct current. But you can also generate electricity through a generator. And that's how electricity comes to our house. There's a power plant where, by different ways, there's a magnet that gets spun. And you spin this magnet, and it turns out that the magnetic field, the magnets, can kind of either push or pull on the electrons. And so as you, let's say the North Pole comes down here, the electrons in this loop of wire can be pushed, and let's just say they're going to be pushed in this direction. And then as the South Pole swings around, the electrons can be drawn back towards the magnet, and the cycle continues as the magnet spins. That generates a current that moves back and forth. It alternates in one direction, then in the opposite direction, and we call that alternating current, or AC. And it works this lamp pretty much the same way. The electrons enter into the little wire, and they attempt to go in one direction, and there's a lot of resistance in this filament, and then the current switches the other direction, so they move in the other direction. They still meet a lot of resistance, and they bounce back and forth. And as the electrons try to move through this wire, they start heating it up, and heat it white hot, and it glows. Okay, so fundamentally, electricity and electrical energy comes from motion, the motion of electrons. And there's two ways to make these electrons move: in a steady flow in one direction throughout the current, throughout the circuit, or oscillate it back and forth. Direct current versus AC, alternating current. We should also be aware that there's at least two ways of setting up a circuit. Back up here, we just talked about connecting the battery to the light bulb, or the generator to the light bulb, and we had to allow for a route for the electrons to leave the source of electricity and make its way back in. And that's because charge is neither created nor destroyed. If we want to have one power source, power multiple devices, well, then we have a couple of ways we can set them up. We can set them up in series, a series circuit, where you just put one light bulb after the other and just have the electricity run straight through, in through one bulb, then into the other one, and then to the third one, and make its way back to the battery. Or you can set things up as a parallel circuit. And this is where you give each device, a light bulb in this case, its own pathway. So there's a wire that connects this light bulb, and the electricity runs through in this direction. And then we give the second light bulb its own path. There's another wire that connects it and brings it back to the battery. And then the third light bulb has its own path. And we say that the devices, the light bulbs in this case, are aligned in a parallel circuit. And if you have one light bulb after the other, then you have them hooked up in a series. Now there's advantages and disadvantages to both. In a series circuit, if you line up one device after the other, then the resistance is going to increase. So as the electrons flow through one light bulb and get slowed down, they exit the light bulb, they're a little bit slower, and then they hit the second light bulb, slow down even more, right? So they're just getting more and more resistance as they make that one path to the battery. By Ohm's law, where current equals voltage divided by resistance, in a series circuit, the resistance is increasing, which causes the current to decrease. And the net effect then is you get less current flowing through all three light bulbs, and that causes them to glow more dimly, less brightly. Furthermore, another disadvantage is if one light bulb blows, that breaks the circuit and no electricity can flow. So if this first light bulb, the filament overheats and melts, and so that there's a gap and electricity can't get through, well, that means electricity can't go through the entire loop, and it will turn off the other light bulbs. The whole circuit is then open or dead. That's different from a parallel circuit. In a parallel circuit, each device has its own pathway, and because you have multiple pathways, you have more current. So if you just think about how many electrons are flying out of the battery, let's actually put it on the negative side. The electrons fly out of the battery. There has to be enough electrons to go into the first path, the second path, and the third path. So right as the electrons leave, there's going to be a lot of them coming out. If you connect a fourth light bulb, well, then you create another path, and now you have an additional number of electrons that have to come out of that battery. And so the more pathways you have, the more current you have. And so there's more current coming out of the battery total, and that results in your light bulbs all increasing in brightness. there is more current flowing throughout the entire circuit, and so they glow more brightly. Now, if one of the light bulbs burns out, well, that causes an open circuit and a breakdown of one pathway. So if the light bulb breaks here, then the electricity can't run through this pathway, but the other circuits, the other pathways are still available. They're still forming a closed loop to the battery, and so the other bulbs will remain lit. So that's a good thing. You don't shut down all the light bulbs if one blows. But then there is a danger that as you add more and more light bulbs, you're going to increase more and more current, and now you run the risk of overheating the circuit, overloading the circuit, and you might have a fire. Okay, last idea is electrical power. We can measure the electrical power by just taking our values of current and voltage and multiplying together. We get a new unit called the watt, symbolized with a W. So you probably heard of a 100-watt light bulb, and maybe you have a feeling that a 100-watt light bulb would glow more brightly than, let's say, I don't know, a 4-watt light bulb, something you might find in a night light. So yeah, the wattage actually gives you a feel for how much power is being used. And then for some of the homework problems, we're going to need to know that definition, that power is a measure of how fast energy is being transferred. And back in chapter 3, if you want to learn more about it, we also define power as the amount of work done per unit of time. So if you do something with a lot more power, well, then you get a lot more work done in a shorter amount of time. Okay, that's all for now. Thanks.